Okay, so in this video I'm just basically gonna do inverse of matrices. So now I'm gonna use first example. So I'm gonna use an identity matrix to find an inverse. Let's say we have matrix A, which is given by 4, 3, 1, 7. Let's say we have a matrix given by this a 2 by 2 matrix like this. Now, in order to find if the inverse exists of a matrix, what we have to know is like the determinant of that matrix must exist. Therefore, that means that A will be a square matrix. And therefore, you can only find the inverse of a square matrix. And another thing you need to keep in mind is that determinant of A cannot be equals to 0. We'll get to this part later. Now here, when we use an identity matrix to find an inverse, we're just going to write A and its identity like this. And then we have 4, 3, 1, 7. And then the identity of a 2 by 2 matrix will just be 1, 0, 0, 1, as I introduced earlier. Now, what we want is to obtain an identity on the left. That's what we want. And then on the right, we'll get the inverse of that. Okay, so how do we obtain that? Okay, first things first, we want to make this to be 0, right? So that means that we'll replace row 1 with row, let's say row 1 minus 3 over 7 row 2. Now, the thing is, like, we're going to use rows to, like, eliminate this. We're going to use rows, and you cannot replace row 1 with something that doesn't have to do with row 1. So whenever you replace row 1, you must have something that has to do with row 1. And now, what we want also is to have 0 here. What we're going to do is, like, replace row 2 with row 2 or row 1 minus 4 row 2. We can do that replacement like that. So now what we're gonna have is like we're gonna have 4. Now we are replacing row 1 with row 1 minus 3 over 7 row 2. So we're gonna have 4 minus 3 over 7 into 1. Now what's 4 times okay, let me just write it down. We have 4 minus 3 over 7 into 1. Now 4 times 7, that's gonna be 28. 28 minus 3, that's gonna be 25, and then we have 25 over 7. So here we're gonna have 25 over 7. And now 3 minus 3 over 7 times 7. 3 over 7 times 7, it's going to be minus 3. So we have 3 minus 3. That's just going to be 0 here. And we do the same. Row 1, it's 1 minus 3 over 7 into 0 now in this case. So we're just going to have this one to be 1. It stays the same. And then this term here, we have row 1 here as 0. So we end up with 0 minus 3 over 7. And 0 minus 3 over 7 into 1. That's just going to be minus 3 over 7. And then what we want also is to have 0 here. So we're going to replace row 2 with row 1 minus 4r2. Again, we replace row 2 with something that has to do with row 2. Okay, so now we have row 1, which is 4, and we subtract 4 row 2. So we're going to have 4 minus 4 into 1. That's going to give us 0 here. And then we're going to have 3 minus 4 into 7. And 4 by 7 is 28. And then 3 minus 28, that's going to be minus 25. And then row 1 minus 4 row 2, so it's 1 minus 4 times 0, which is going to give us 1. And then we have 0 minus 4 into 1, which is just going to give us minus 4. And now we're pretty much close to obtaining what we want. And now we want to have 1 here. We want to have 1 here, and the only way we can have 1 without changing this one as 0 is if we replace row 1 with 7 over 25 row 1. And then here we want to obtain 1 as well, so we can replace row 2 with minus 1 over 25 row 2. So when we do that, replacing row 1 with 7 over 25 r1, 25 over 7 times 7 over 25, that's going to be 1. 0 times 7 over 25 is going to be 0. 1 times 7 over 25 is going to be 7 over 25. And then minus 3 over 7 multiplied by 7 over 25, that's just going to be minus 3 over 25. And then 0 times minus 1 over 25 is going to be 0. Then minus 25 times minus 1 over 25, that's just going to be 1. And then 1 times minus 1 over 25, that's just going to be 1 over 25. And then minus 4 times minus 1 over 25, this one will be negative, minus 1 over 25, since we're just saying 1 times minus 1 over 25. And then now minus 4 times minus 1 over 25, that's just going to be 4 over 25. And so we have an identity on the left now. That means that we have A inverse on the right. So that means that A inverse will just basically be 7 over 25 minus 3 over 25, and then minus 1 over 25, and then 4 over 25. So that's how we can like find the inverse of this. It's basically really simple, really. Okay, so now try this one. Pause the video and see if you can like evaluate this this one. 2 3 2 3 2 3. Trying to see like if you can like okay, let me just say this one is minus 3. Pause the video if you and see if you can like evaluate this one here. So now what we want is to use the identity and find the inverse of that. So now we have 2 minus 3 2 3, and then the identity of a 2 by 2 matrix is 1 0 0 1. And now we want to make this one to be 0, right? We want to make this one to be 0. How do we do that? So now if we look here, if we add the two equations, then the first one is going to be 0. So replace row 1 with row 1 plus row 2. And what we're going to do is like we want this one to be 0 now. So what will we do if we want this one to be 0? Remember, we want the identity on the left. So we can replace row 2 with row 1 minus row 2. So when we do that, here's what we're going to have. When we do that, we have row 1, we are replacing it with row 1 plus row 2. So we have 2 plus 2, which is giving us 4. And then we have minus 3 plus 3, which gives us 0. Then we have 1 plus 0, which gives us 1. And then we have 0 plus 1, which gives us 1. And then we're replacing row 2 with row 1 minus row 2. Then 2 minus 2, that's 0. Minus 3 minus 3, that's going to be minus 6. And then 1 minus 0, that's 1. 0 minus 1, that gives us minus 1. And then now that we have this, we want to make this one to be 1. So we can replace row 1 with 1 over 4, row 1. And then we want this one to be 1, so we can replace row 2 with minus 1 over 6, row 2. And then we have 4 times 1 over 4, that's going to give you 1. And 0 times 1 over 4, that's going to be 0. 1 times 1 over 4 is going to be 1 over 4. 1 times 1 over 4 is going to be 1 over 4. And then replacing row 2 with minus 0 times minus 1 over 6 is going to be 0. Minus 6 times minus 1 over 6 is just going to be 1. And then 1 times minus 1 over 6 is going to be minus 1 over 6. And then minus 1 times minus 1 over 6 is just going to be positive 1 over 6. Now we have an identity on the left. That means that we'll have an inverse on the right. So that means that if we have our matrix to be this one, that means that A inverse will be equals to 1 over 4, 1 over 4, minus 1 over 6, and 1 over 6. So that's basically what we're going to have here. So that's the inverse. Really, it's not really that complicated. You're just using the rows to manipulate that to get an identity. So now by definition we know that A multiplied by A inverse, by definition A multiplied by A inverse will give us an identity matrix. Okay, now can we derive a formula from this? Okay, let's generalize. I know, like, using identities to do this can be confusing for some people. But now let's say I want to derive a general formula with you guys here. Okay, so now let's do this. Let's say A is given by the entries A, B, C, D. The matrix A has entries like this. Now, what we want is to derive a general formula of finding A inverse. What's A inverse, right? Now we just have variables. The thing is, when we work with variables, we just generalize the case. We can basically use that to solve any other case that we have. So that's basically what we want to do, is we want to obtain a general formula from that. We want to derive a formula. That's why we use variables instead of just numbers. But what we know is that A multiplied by A inverse will just give us an identity matrix. That's what we know. So now we're going to use this definition to like find A inverse. Now what I'm going to do is let A inverse have the entries E, F, G, H. Let A inverse have the entries E, F, G, H. Let A inverse have the entries E, F, G, H. And what we do from that? Okay, so now we have A multiplied by A inverse. And I said A is denoted by A, B, C, D. And now we have A inverse. A inverse will just be denoted by E, F, G, H. And we know that that will give us an identity matrix, which is just 1, 0, 0, 1. That's what we want to obtain from that. So now, what we do when we multiply two matrices together. So we're just going to have AE plus BG That's the first entry of that matrix, of the new formed matrix. And then we have CE plus B, DG, I mean, plus DG. And then when we proceed with that, we're gonna have like AF plus BH. Then when we proceed with that, we're gonna have CF plus DH, and this will give us 1001. That's what we're gonna have. Like, so now two matrices, notice that we get a matrix here and we get a matrix here. Now two matrices are equal only if the corresponding entries are equal. So what does this mean? This means that AE plus BG equals 1. This implies that. And now that means, like, if we solve for G, let's decide we solve for G, we know that BG would be equals to 1 minus AE, right? Okay, let's just leave it there. Now CE plus DG will be 0. CE plus DG equals to 0 because we're just corresponding the entries here. And now what does this mean? This means that DG equals minus CE. Minus CE. Then if we solve for G, G will be equals to minus CE over D. Then we can plug that there. So now we have BG, B into minus CE over D. This will be the same as 1 minus AE. Now we want to solve for E, so we're just going to multiply everything with D, every side with D. So we have minus CE minus BCE equals D minus ADE. And then from then we want to solve for E, so we can take E this side, and then we'll have ADE minus BCE equals D. And then from then we just are gonna vector by E, then we have E into AD minus BC. Then this will be equals to D. And then this means that E equals D over AB minus BC. And if we look at AB minus BC, what's AB minus BC? I mean, AB, sorry, here's just a typing error. We're just gonna have AD, I mean, AD, because basically we're just taking this one and factorizing by E. Okay, so AD minus BC is just a determinant of A. So that means like E will be equals to D over determinant of matrix A. Okay, so now when we plug that there, we get G equals minus C, and E it's D over determinant of A. And then we divide that with D. So we just plug in E here. And then when we simplify this, we get G equals minus C over determinant of A. So now we have solved for E and G. We have solved for E and G. Similarly, what we can do is like solve the values of F and G. You can do that. AF plus BH equals 0 and CF plus DH equals 1. And when you solve that, you get F equals minus B over determinant of A. That's what you're going to have here. And when you solve for H, you're going to get H being A over determinant of A. So that's what you're going to have. So this means that we found the inverse. If A is given by the entries A, B, C, D like this, then that means that A inverse will be given by now remember it's E, F, G, H. In this case E, it's D. So you'll have D over determinant of A. And then G is given by minus C over determinant of A. Minus C over determinant of A. And then B is given by, in this case B was F, and we solved for F when we found minus B over determinant of A. And then the last one, which is H, was given by A over determinant of A. So we'll have something like this. You'll have something like this. Now you can take 1 over determinant of A outside. So you'll have 1 over determinant of A outside, and then you'll be left with D minus B minus C and A. So this is the general formula of finding an inverse of a matrix. That's why the determinant must exist and it cannot be equals to 0, because we are basically dividing by that. That's the proof. Okay, let's try some practical examples with this proof. Okay, so let's say we have a matrix 1, 5, 1, 1. what's the inverse of this matrix? That's what we want. So at first you'll find the determinant of that matrix. Determinant of A, which is just 1, 5, 1, 1. We're going to use the diagonal rule, 1 times 1, which is just going to be 1. Or let me write it down, minus 5 times 1, which this is just going to be 1 minus 5, which gives us minus 4. And then that means that A inverse will just be equals to 1 over minus 4 into this 2 switch. So this one you'll put it there, and then we'll have 1, 1. Since they're the same, switching them doesn't change anything. And this one's just swap the signs. Then you have minus 1 and minus 5. And then distribute this inside. Then you have minus 1 over 4. Then minus 5 times minus 1 over 4 is just going to be 5 over 4. And then minus 1 over 4 times minus 1 is just going to be 1 over 4. And minus 1 over 4 times 1 is just going to be minus 1 over 4. So that's how you find the inverse of that. Then if you have another one, let's say you have A equals 0, 0 and 0, 2. Can you find the inverse of this? Since like if you find the determinant of A, this will be 0 times 2 minus 0 by 0, which is just going to give us 0. Therefore, A inverse does not exist. That's all the things that you should familiarize yourself with. We cannot find the inverse if the determinant is 0. So basically dividing by the determinant, we're not allowed to divide by 0. So now, try this example. If we have 5, 4, 3, 4 times 3, 12, 5 times something. Let's say this is 4 as well. And then we have 3 here. Find the inverse of this matrix. So the inverse of that, we have to first find the determinant of A, which is just 5 times 3 minus 4 by 4, which is just going to give us 15 minus 16, which gives us minus 1. And then this implies that A inverse will be equals to 1 over minus 1. And now this 2 switch, so you'll have 3 here and 5 here. And then this ones, they just swap signs. So you'll have minus 4 and minus 4. Then distribute 1 over minus 1 is minus 1. Then distribute it inside. Then you just make everything negative if it's positive. And if it's negative, you make it positive. And then that's it. Then you have minus 5. That's the inverse of that. So technically, it's not that complicated, really. So you now have 2 methods of solving a 2 by 2 matrix. And using the identity matrix, you can also go for a 3 by 3 matrix inverse.